We should first check whether the adjustment parameters of the VECM have correct signs and values. We need to do this to ensure that the variables will converge back to long-run equilibrium. If the signs or values are incorrect, the model breaks down because the long-run equilibrium relationship will not hold. This will clearly indicate that the model is misspecified. This could happen due to several reasons, such as the variables might not be cointegrated or the number of cointegrated relationships might be incorrectly specified. Even misspecified trends and constants can have a huge impact on the results. In our example of demand for money, we already discussed the adjustment parameters. We observed that our model will converge back to long-run equilibrium. Even though the adjustment parameter for IBO was insignificant, the equilibrium will be restored because the other variables will adjust. Adjustment parameters for LRM, LRY, and ID had correct signs and values which will ensure convergence. Remember how we defined cointegration in Tutorial 1. We discussed that the variables might be non-stationary, but if cointegration exists, the linear combination of those variables will have a lower order of integration. For instance, if the variables are integrated of order 2, their linear combination will produce I1 residuals under cointegration. Similarly in VECM, the cointegrating vector must have a lower order of integration than the variables. Since we generally use VECM on I1 variables, we expect the cointegrating vector to be stationary. Therefore, after estimating VECM, we must ensure that the cointegrating vector is stationary. If it is non-stationary, then the VECM is misspecified. In Stata, it is easy to predict the cointegrating vector. We can use the predict command to accomplish this. In the command shown here, the cointegrating vector is just the variable name and we can name it anything. The option CE tells Stata to predict the cointegrating equation. The option equation is used to specify which cointegrating equation we wish to predict. In our example, we only have one cointegrating equation, so we simply specify _CE1. If we had more cointegrating equations, we can predict them one at a time by specifying _CE2, _CE3, and so on. In R, we have to predict the cointegrating vector manually. It is still easy because we simply have to use the coefficients and variables as they are in the results. In our example, we can do this using the command shown here. The cointegrating vector is the name we are assigning it. Then, we simply calculate it by putting in the variables and their coefficients. Now that we have calculated the cointegration equation, let us see if it's stationary. If we look at the plot of the cointegrating equation, we do not see any trend or sudden breaks in it. There does not seem to be any indication that it might be non-stationary. We can also verify that using any tests of stationarity. For instance, let us take a look at the results of the ADF test applied to the cointegrating equation. Here, we have not included a drift or trend component because they were insignificant. Also, the lag length for the ADF test was chosen using AIC and BIC. The coefficient for the lag is negative and significant. The p-value is also less than 0.05, which means that we reject the null hypothesis of unit root. Hence, we can conclude that the cointegrating equation is stationary. We must make sure that the model does not suffer from autocorrelation. If we observe that the residuals are autocorrelated, we must increase the number of lags in the VECM model. To test for autocorrelation in Stata, we can use the VECM command to apply the LM test. The null hypothesis of the test states that there is no autocorrelation. We also have to specify the maximum number of lags to consider for autocorrelation. There is a lot of debate on how to correctly specify the number of lags. It generally depends on the sample size, type of data and analysis. Here, we have quarterly data with 55 observations and Stata uses the LM test. So, we will specify 8 in lag option and show its results for illustration. This command automatically converts the VECM model into its underlying VAR model and tests for autocorrelation. This procedure is valid because the residuals in VECM and its underlying VAR model are identical. In R, we have to manually convert the VECM model into its underlying VAR model using the VEC2 VAR command from the vars package. In this command, we input the CA.JO object we estimated for the Johansen test and specify the number of cointegrating vectors. Now, we can apply the test of autocorrelation using the underlying VAR model. The serial.test command from the vars package can be used here. In the command shown here, var form contains the results of the underlying VAR we converted from our VECM. The option type allows us to choose among 4 types of tests of autocorrelation. PT asymptotic applies the portmanteau test and PT adjusted applies the adjusted portmanteau test for small samples. Generally, we do not use portmanteau tests for VECM because the degrees of freedom are not correctly specified for a VECM and their asymptotic properties cannot be justified. We only use these if we have to test up to a large number of lags. We will focus on the Brush-Godfrey LM test for our VECM. The BG applies this LM test, whereas the option ES applies the small sample correction of the LM test. We are inclined to use the ES option as we have a relatively smaller sample. The option lags.bg will allow us to specify the maximum lag of 8 that we are considering for illustration. Here, we have shown the results of the LM test using the ES option with 8 lags. The results indicate that there is no autocorrelation. Therefore, autocorrelation does not seem to be a problem in our VECM model. Suppose, if we observe some autocorrelation, then we will have to increase the number of lags in our model till the problem of autocorrelation is eliminated. Next, let us check the stability condition of our VECM model using eigenvalues. This test helps us check whether the number of cointegrating vectors is misspecified or the cointegrating equations are not stationary. To conduct this test, we have to convert the VECM coefficients into VAR coefficients and construct a companion matrix. The eigenvalues of the companion matrix show us if there is any misspecification in the number of cointegrating relationships or if they are not stationary. The stability condition for VECM states that there will be K minus R unit moduli. Here, K is the number of endogenous variables and R is the number of cointegrating relationships. In our example, K is equal to 4 and R is equal to 1, so we should have 3 unit moduli in the companion matrix. If the modulus of any other eigenvalues is 1 or greater than 1, then the number of cointegrating vectors is misspecified or the cointegrating equation is not stationary. In Stata, the VECstable command takes care of everything automatically. This means that it converts the VECM coefficients to VAR coefficients, constructs the companion matrix from those VAR coefficients, estimates the eigenvalues and shows us the results. The graph option can be used to make a plot of the results. However, the plot is not necessary because it does not give us any additional information. In R, however, we have to do all these steps manually. That is, we have to obtain the VAR coefficients, which we already did using the VEC2 VAR command. After that, we have to construct the companion matrix from those VAR coefficients. Let us see what the companion matrix should look like. The companion matrix is a combination of all the coefficient matrices of the underlying VAR model, identity matrices and null matrices. Since the underlying VAR has one more lag than the VECM, we will have one more coefficient matrix in the VAR form. That means that if the VECM has 3 lags, then its VAR will have 4 lags. In our example, VECM has 1 lag, so our underlying VAR has 2 lags and 2 coefficient matrices. We have to combine these 2 coefficient matrices with an identity matrix and a null matrix as shown here. Since we have 4 endogenous variables, all these will be 4 by 4 matrices. Our identity and null matrices must also have the same dimensions, which are 4 by 4 in our example. To construct the companion matrix, we append all the coefficient matrices by columns. Then, we append the identity and null matrices by rows and columns as shown here. In our example, we will append the two coefficient matrices side by side. We will have to append the identity matrix below the first coefficient matrix of lag1. Moreover, we will have to append the null matrix below the second coefficient matrix of lag2 of the underlying var. Once we have the companion matrix, we can easily calculate the eigenvalues using the eigenfunction on the companion matrix. Then, we apply the mod function to estimate the moduli of those eigenvalues. The results of this procedure will be the same as the vectable command in Stata. Let us take a look at the results and check for any misspecifications. To interpret the results shown here, we have to consider the stability condition mentioned earlier. It states that we will have k minus r unit moduli. In our example, k is 4 and r is equal to 1. So, we should have 3 unit moduli because k minus r is equal to 3 in our example. The results here show that we have 3 unit moduli as expected. All the other moduli of the rest of the eigenvalues of the companion matrix are nowhere close to 1. Therefore, the VECM satisfies this stability condition. We have no evidence or reason to suggest that the number of cointegrating vectors is misspecified or the cointegration equation is not stationary. To test whether the residuals from VECM are normally distributed, the Jark-Barrett test is often used. This test is based on skewness and kurtosis of the residuals. To be normally distributed, a series should have 0 skewness and kurtosis should be 3. Therefore, the skewness, kurtosis and Jark-Barrett test use this information to test for normality. In VECM, we can apply the Jark-Barrett test to the residuals of each equation one by one. These are known as the univariate Jark-Barrett tests. The null hypothesis of the univariate test is that the residuals for that equation are normally distributed. We can also apply the multivariate Jark-Barrett test, which jointly tests the normality of residuals for all equations in the VECM. The null hypothesis, in this case, is that all the residuals of k equations have a normal distribution. For skewness tests, we test the null hypothesis that the skewness is 0, which indicates normal distribution. On the other hand, the null hypothesis for the kurtosis test is that the excess kurtosis is 0. If we reject the null hypothesis in any of these tests, it indicates that the residuals may not be normally distributed. In Stata, the VECM command automatically computes and reports the univariate and multivariate Jark-Barrett, skewness and kurtosis tests. The option DFK can be used to apply small sample adjustment to the tests. In R, the Normality.Test command can be used for this purpose. We can specify the option multivariate.only is equal to false to estimate both univariate and multivariate tests. The var form shown here is the var formulation of our VECM model that we obtained using the vec2 var command. This is acceptable because the residuals of VECM and its underlying var are identical. If we look at the results of normality tests, we can see that we cannot reject the null hypothesis of all the multivariate tests. This indicates that the residuals are normally distributed. In the case of univariate tests, the residuals of all the equations indicate normality except the LRY equation. This brings us to another important consideration. The VECM coefficients are still consistent even if the residuals are not normally distributed. In some cases, we can proceed with the model even if the residuals are not normal. For instance, in some cases, we might be interested in forecasting performance rather than inference. In our example, we are not too focused on the LRY equation, and all the other tests indicate that the residuals are normal. Moreover, other goodness of fit tests indicated that the model is not misspecified. The autocorrelation test showed no evidence of autocorrelation. The stability test indicated that the number of cointegrating vectors is not misspecified, and we also observed that the cointegrating equation is stationary. As a result, we can move on to forecasting and impulse response functions. Thank you for watching, and I will see you in the next tutorial.